Khalil from the Zewail Institute of Science and Technology. And he's going to tell us about TeV scale, supersymmetric B-L.
Yes, thanks. So this is based on some work I did in collaboration with Stefano Murati and my student Alex. So in fact, B-L extension of the standard model is well motivated from bottom-up approach to account for the light neutrino masses. And as we will see now, you don't need really to have the U1 B-L at very high scale. It could be at TeV scale as well. And this model can account for this neutrino masses, and at the same time can give very interesting signatures at LHC because it contains, by construction to make the U1 B-L anomaly free, contains 3 singlet fermions, which we call dry-handed neutrinos. And of course, there is a gauge boson associated with the U1 B-L, and also extra singlet scalars to break this U1 B-L. Apart from the low bottom-up approach or the bottom neutrino motivations, there is also some up-down motivations, because B-L usually obtained from the construction of intersecting deep brains, for example, as we have seen today and other days. This type of constructions of intersecting brains, usually you cannot get the standard model, just the standard model, but you get the standard model across the U1 B-L, because you have stacks of brains which is giving you U1, U3 and U2 from another stack of brain cross U1. Then you have 4 extra U1s, these 2 U1s plus extra 2 U1s here, because U3 is isomorphic to SU3 cross U1. In fact, 2 of these 4 associated U1s are non-anomalous, and they are exactly the hypercharged U1 and the B-L U1. So the B-L in this sense, extension of the standard model in this sense, is also motivated from deep brain construction. In fact, some time ago, Overt and his collaborators proved that strongly coupled heterotic strains also you cannot get just the standard model, but usually you get the standard model cross U1 B-L. Moreover, recently, Fernando and his collaborator also showed that the SUSY B-L can be obtained from some construction of brain models. Gut models, usually B-L is broken on the way down to the standard model. However, if you start with SO10 and you break it via this singlets in the 54 hex to Battisalam, and then you break Battisalam not by fundamental to reach the left-right symmetry, but by this adjoint 1513, you will get SU3 cross SU2 cross U1 B-L. And then you need a singlet 1102 charged under this U1 B-L by 2 units to break down to the standard model. And this is exactly what we considered in our model from bottom-up approach. The point now, is it necessary that we break B-L at high scale, or can be TeV scale? In fact, breaking symmetry in general can be at any scales. For example, the electroweak symmetry breaking in the standard model, we don't know exactly where the electroweak is broken unless we embed the standard model in supersymmetric extension of the in MSSM. Then we studied the radiative symmetry breaking, and then we proved that the electroweak is broken at 100 GeV. And we did also the same. We implement the we embed the B-L extension in supersymmetry, and then construct the minimal supersymmetric version of this model. And now we have 2 singlets, heads, chi1 and chi2, and we have to give soft terms positive mass square for this chi1 and chi2, and then try to study the normalization group equation, to study the evolution of this scalar fields, and see at which scale they will get non-vanishing negative values, negative pairs. And in fact, also because we have right S neutrino can also break up a wave, and we can break the symmetry. This is usually happening in some models, but in this case it will break also our parity, which we would not really prefer. But we also consider in our running, and then we start to study the normalization group equation of chi1, chi2, and the S neutrino. And as you can see, the chi1, which coupled with right-handed neutrinos, is exactly getting a wave, getting minus mass squared about TeV scale. This is a scale squared, so about 10 to 6 means around TeV. So at this point, we started to believe that the V minus L can be radiatively broken at TeV scale, and then we could have also some kind of radiative symmetry breaking condition. So we determine mu prime exactly like mu term in the star MSSM. Now we have mu prime, and we define a kind of tangent beta prime for this model. Now, if we are convinced that B minus L can be broken, especially if it is within supersymmetry at TeV scale, is it possible to implement to account for the light neutrino masses? In fact, yes, because now we have the Majorana mass term will obtain from this Yukawa coupling. So when chi get a wave, and this will be of order TeV, as we said, because it is now everything is given in terms of the wave of the B minus L breaking B prime. And also we have a Dirac mass term which will be of order the electroweak. So we can construct this matrix, type 1 SUSY mass matrix for the neutrino, which give light neutrinos of order m Dirac square over m right handed. And now, usually m right-handed neutrinos taken 10 to 13 GeV to get the m Dirac mass of order 100 GeV. Now we have m right of order TeV. So the price we have to pay at MD, in fact, should be of order 10 to minus 4 only. So 10 to minus 4 means of order of the electron mass. So it's not that a big price we have to pay to work with TeV scale SUSY or TeV scale B minus L. So in this sense, you could have TeV scale B minus L, and your Dirac mass matrix, or the Dirac mass neutrino mass should be of order the electron mass. And in fact,
Actually,
all this.
You mean the muon mass?
Why? Yes.
That's 100 MeV, no?
Oh, Dirac electron mass.
Oh, sorry, 10 to minus 4 GeV.
10 minus 4 GeV. So also there is an interesting signature at LHC for this class of model. At least now you have the gauge boson, the Z prime. You can produce the right-handed neutrino in pair, and then this right-handed neutrino, because in this class of model has small Yukawa coupling, as we have seen, 10 to minus 6 because the mass over the pair. So 10 to minus 6 means this makes this particle somehow long-lived particle. So the signature here that it will not decay immediately, but we can observe kind of displaced vertices. So the vertex of the production will be displaced from the two vertex of the annihilation. And then it will eventually annihilate to 2 dileptons plus missing energy, which is very interesting signature because it has essentially clean background. To avoid this mass, small Yukawa couplings, Dirac neutrino Yukawa coupling, which is 10 to minus 6, as I just mentioned, you can also keep everything as it is, and you can believe that B minus L is a TeV scale, but you can use another mechanism for breaking, another mechanism for generating the neutrino masses. So we could, for example, instead of type 1 SUSY, we can consider what's called the M versus SUSY mechanism. Inverse seesaw, you try to avoid the mass term of the right-handed neutrino, and you try to add another field which coupled with a right-handed neutrino so that you construct this 3 by 3 mass matrix. Now with this 3 by 3 mass matrix, the light neutrino mass will be essentially mdx squared times the mu s divided by mn squared. Now, so if mu s is rather small, you can keep md as large as you want, and still you get m light neutrino of order electron volts. This is a standard scenario in neutrino masses generation. Is called the inverse seesaw. So you need essentially mu s. It is a relative size of md and the mu s. But if you decide to take md of order the electroweak wave, which is 100 GeV, then you need mu s to be somehow 10 to minus 6, and this can be obtained radiatively. Now, the supersymmetric version of this model, because I wanted to discuss the implementation of this model at the Higgs mass correction. So the SUSY version of the B minus L with inverse seesaw, we will have, beside the light left-handed S neutrino, you have now a couple of right-handed S neutrino, the right-handed S neutrino and tilde, and this what we called S tilde. And in fact, we heard this week that the Higgs mass, which is of order 125 GeV, is somehow rather high for the MSSM, and it could make severe constraints on the parameter space of the MSSM. Now you need to push essentially all your masses to satisfy this, because in minimal SOGRA you need to have M naught of order couple of TeV and also M1/2. In fact, in this model, in SUSY B minus L, you will not have, you can relax all these constraints because you will have now new contributions similar to the S-top contribution at the one loop for the Higgs mass. You can have also another contribution coming from right S neutrino loop corrections. So you know that in the Higgs, and the MSSM is getting 3-level mass of order mz, and then one loop corrections, which is proportional to m top to power 4 divided by the wave square, essentially. Now, this is give the mass of order, in principle, if you go up to several TeV S top, then you will get the mass of the Higgs around 135 GeV. But as I said, in fact, also second two loops reduce this is around 230. But as I said, this requires somehow heavy stop to get this value. Now, beside these two contributions, 3-level and 1 loop from MSSM, now you have significant contribution from right S neutrino, because right S neutrino coupled with the Higgs with large Yukawa coupling in this inverse seesaw. So you will have this 3 loops similar to the top and S top, exactly neutrino and S neutrino. We calculated this using the usual procedure where compute the one loop, and here also there is no hierarchy in the Yukawa couplings of the right-handed neutrinos with the Higgs, not like the top. The top, it was the only particles from the up quark sectors is relevant for the Higgs correction, because the Yukawa coupling of the other two generation is rather small. Here we have a factor 3 also, which even compensates the factor 3 of the colors in the top S top. So making these calculations, and in fact now we will find that essentially for some limits of MA much larger than MZ cosine 2 beta of order 1, you will find that MH is given at the usual 3-level contribution MZ, and then the top contribution effects, and now some also delta neutrino, S neutrino effects, which is of the same order more or less of the top S top contribution. So to give an example, if you take the masses of order 1 TeV and the Yukawa coupling is of less than 1, and the not very heavy right-handed neutrino, just 500 GeV or so, you get this contribution also of order 100 GeV square, similar to the top S-top contribution, and therefore now you can push your mass of the Higgs mass to rather heavy, to be even of order 170. Of course, we don't need to push the Higgs mass to 170, but we need to relax now all the constraints on the parameter space of the MSSM, because now if you have extra contribution like this, you don't need really to push the top S-top to up to 100 GeV as it was before. So this is some examples of how we can enhance the Higgs mass in this model if we keep the S-top with its maximum value. So you can go from 140 up to, as I said, 170 or so. Also the A term could play some rules because the large off-diagonal mixing. And this is the main results in this type of model that I would like to present. So if I have some few seconds to summarize. Okay, so I wish I convinced you that the B minus L extension of the standard model is well motivated from bottom-up approach by neutrino masses and from up-down also by some construction from deep brains or from ground unifications. And it has new particles, so it could have very interesting signature at LHC, especially this dileptons signature. And in fact, it could help in, in accommodating the new results of the Higgs mass without severely constrain the parameter space of MSSM. Something also I haven't discussed, that the right-handed S neutrino could be interesting candidates for the dark matter and then solve another problem of the MSSM, that the dark matter range of the LSB is essentially closed. Thank you very much.
So, I mean, your Yukawa coupling for the neutrino is order 1, right?
Yeah, I'm saying order 1, but it's not exactly 1 because you have to be careful with.
I mean, it will give rise to some lambda.
Yeah. You have to be with what?
Because if it's so, I mean, if it's order 1, it will. I would imagine that it gives a Landau pole before the.
No, we take into account we check also, we consider the top Yukawa coupling running, and we avoid any. No, I'm making order 1, but kind of 0.8 is enough to avoid this Landau pole.
Yeah, so your Yukawa coupling is 0.8 or
yeah, in the diagrams, yes.
Okay, let's thank Shaaban again.